Hello, in this session we will design pre-stressed concrete beam, which is a pre-tensioned concrete beam with AASHTO type 6 section, and it will have a slab thickness of 200 millimeters. The strength of concrete is 50 megapascals for the beam, and for the slab will be 30 megapascal. We are using 20 reinforcing bars of grade 400W, and we will have pre-stressing strands with the grade of 1860 megapascal. The jacking force will be 75% of the maximum stress, and pretension is applied at initial pretension stage. So to start the project, we first go to new project. Project configuration. To define the configuration of a pre-stressed beam or structure, we go to this tab. The project will have construction stages, so we need to put the check mark on this option here. We are going to use stage 1 as pouring of concrete, stage 2 end of cure, stage 3 transfer of pre-stress. Also we will use stage 5 for addition of slab, stage 6 as end of humid cure for slab, and stage 8 and 9. So because we don't have post tensioning, I'm going to remove this check mark. So these are the stages that our project will be analyzed and designed. For the day values here, the first ones, the default values are okay. But for stage 5, I'm going to change it to 60 days. And stage 6 will be 7 days later, 67. For stage 8, I'm going to use the same, 67 days. And the long term, we're going to use 1000 days. So these are the stages and the dates. For the shrinkage and creep model, I'm going to use the S6 2006, and relative humidity is 70%. And for the others, I'm going to just keep these default values. And for exposed surfaces, we have the top surface, these bottom ones, and here the size of the beam will be exposed. So these values are okay, so click OK. At the next stage, I will define the materials used in this project. So first I will define the concrete, so common materials, concrete material. We can define a new one if the material that we need to define is a close one to these others. We can just copy and paste it and change the required values. But here I'm going to define a new one. So plus the name will be concrete 50 pre-stressed S6. It will be a public one. If you change this option to public, it means that this custom material that you're defining here in this project, it can be used in your other projects. But if you put it as private, it will not be transferred to other projects. So normally when we define a new custom material, we put it on public to, if we want to use it in another project, it will be available in the other projects files as well. So for the E, 29966. For the G value, I'm going to use 12485. 93. For the Poisson ratio, 0.2. Material density 23.54. Again 23.54. Thermal expansion factor 10. Compressive strengths will be 15. Modification factor 1, 0.02, and factor to calculate pressure concrete I'm going to change it to 0.19. And the type of the cement will be quick hardening. So as you see, we've defined a new custom concrete material. And if you need to get some help on these parameters, you can always press F1. For example, for this alpha value. And here you have the description of this alpha value, which is a factor depending on type of cement and curing condition. It's used in the calculation of prestressed concrete beams. It's used for F'(C). So click OK. In the next step, I'm going to define the slab. So we need to go structure, slab and steel decks. So I'm going to name it slab. Concrete material for the slab is 030. The concrete thickness will be 200 millimeters. And the reinforcing bars for top is 20 amps. Spacing 300, and for the top I'm going to use again 20 amps. For the distance will be 150. For the bottom ones we need 20 amps. 300, 150. The cover and reinforcing material, which will be G13. We can have this info viewed like this. Click the cell, right click detail, so you can have the information also here, and you can modify the information from this window. So the slab is defined here. Okay. Next we are going to check the strands. So we need to common and cables. First, steel grades. So we are going to use this 1860 strands that we already defined here. So if you don't have that material, you need to define a new steel grade for the cables. And also we need to check for the strands. And for the strands we will use this strand type. So as you see, it's already defined here, but if you don't have it in your model, you can always define a new strand type. Okay, now I'm going to build the geometry and the beam itself. So it's a 2-span beam, and I'm going to insert the coordinates using the spreadsheet here. So I'm going to name these as, the first node is N1, it will be a support. going to use these coordinates for N1, for N2 support 27.32 by 4 meters, 0. For N3 28.12. N4, and for N4 support 60.32. These are the coordinates for N4, N5 61.12. Finally, N6 support, and this will be 88.44. Okay, so if you check the nodes here, they are already defined here. As you see, I have 3 spans, and I have some small beam elements that will be cast by slab. So for the first stages, I will have the beams here, pretension beams, and after that, with pouring of the concrete, the extra small beam elements will be activated here between these nodes. So to define the restraints, I'm going to select all of the supports and define them as Rx fixed, to Ry reaction. In this project, I'm going to use an elastic spring with a stiffness of 2000 kilonewton per millimeter. For Rz, it will be fixed, Mx fixed, My fixed, and finally Mc free for all of the nodes. And you see the spring here. And to prevent the instability in the whole model, I'm going to change the first support restraints and restrain the Rx, and we will restrain the Mz to prevent the section to twist or torsional instability. Also, we need to, for these supports, we need to remove this Mx. As free, and also we will free the Mx. if you want to check again the restraints, as you see here, R0 is fixed, RY elastic, RX is free to apply the pre-stressing, and we have MX and MZ free, but we have already fixed it at the first support, and MY also is fixed. And if you zoom on the supports, you will see the conditions of support for all of the nodes here. And the first node, as you see, is closed and prevented for torsion. Okay, for the next step, I will add the members. So we select the member icon and add, and we just click the first node and the end node. The add member dialog box will pop up, and I'm going to name this member as M1. The end conditions will be fixed. The member type will be H2 type 6. Material, we already defined our material, the custom material. For the dead load, we use the predefined load case here. We will activate the design criteria, and because it's a composite beam with concrete section and the concrete slab on top, so we need to select this option here as composite beam. Before clicking OK, we need to define the construction stage for this member, and as I explained before, this member will be activated from stage 2, so we define it as stage 2. We are going to align the section at the top. Finally, in composite beam, I'm going to define my composite section here. I'm going to use the slab that we already defined, and we have no studs here because it's a concrete project. For the effective B, I'm going to use 2600. And I'm going to remove this check mark because we have a staged construction. And for this part, as you see here, the 3 middle beams will have continuous end conditions, but the 2 small beams here, this one and this one, we are going to define them as hinged during construction stages 1 to 5. Also for the concrete, we will define this as D or dV from the face, and this one will be for negative bending moment. So all of the characteristics of the member are defined, so I press OK. And if I use the 3D view, I will have my section here. I'm going to use the same section and properties for the middle spans. Stage 2, the rigid extensions, the composite beam definition, and as you see here, it's fixed. Okay, and the final span. As you see, we have the same characteristics. Okay, and next I'm going to define the small beams which will connect to spans. So these small beams will be activated from stage 5. And also these are okay. For this member, I will change this to hinge because before stage 1 to 5 they are not there, so I don't want to have some restraints on my moment. Others are okay. And finally I'm going to add this member. So again, as you see, stage 5 is okay. Rigid extensions, slab definition, and the hinged one. Okay. So I have my model here, it's defined completely. Geometry and section properties. We also need to define rigid extension at the ends of these span beams here, the large beams, because ADA will use these rigid extensions to put the rebars and place the extension for rebars. So to define these rigid zones, I'm going to use the spreadsheet. We go to members mode, select the spans, large beams, Control H, and here in the connection tab, these two columns that you see here is the rigid extension part for the start of the beam, and this is for the end. So for this I'm going to define it as 150 millimeters, and for the end connection it will be minus 150 according to members local axis. Okay. Next step is to define the load cases for this project. So you go to load cases, definition. I'm going to define 6 load cases. The first one is already here, dead load, but we change it to prefabricated components. S6 prefab components. I'm going to add another one as dead. Stage 5. It will be cast concrete. Dead load stage 8. I'm defining it as cast concrete again. and I will add here some temperature loads, temperature plus, temperature K, and temperature minus. And also an additional dead stage 5, which is prefabricated components. So these are the load cases. And as you see here, we have the dead load automatically calculated here. And also we want to calculate the dead load from stage 5. Automatically calculated. This one will be the self weight from the two middle small beams. So to change those for dead load stage 5, we push OK here, change them, select them, Control H, and for their dead load I'm going to replace it with our dead load stage 5. Okay, so they will not have the same weight or effect from the stage 1, and they will be activated in stage 5. Also for our temperature gradient, we can go to this tab here, temperature, and I'm going to deactivate this option here, which for a positive temperature gradient I don't want to use the snow or ice possibility. So click OK, and right now I'm going to apply the loads. So I'm going to select the members. Firstly, we need to activate the load case. And I'm going to use additional dead stage 5 load case. Save the project. So I will select these members. And apply the loads. So a distributed load of minus 16.18 will be applied to all of the members. Okay. For these two members, I'm going to add two concentrated loads. Using this. The position will be 906. And the force value is minus 27.60. Also another concentrated load, 18.16 minus 27.60. So as you see here, I have my punctual or concentrated loads here applied to the beam. And for the middle beam, I'm going to add three concentrated forces. The first one will be at 802 minus 27.60. Second one, 1605, same value. And third one will be 24.07, the position of the load, and the value will be same. Okay, and again, as you see here, the loads are here, the concentrated loads. Okay, so these were the extra loads for stage 5, extra dead loads. And also I'm going to apply another dead load, which is permanent loads applied at stage 8. So I select stage 8. I select these three span members and apply a concentrated or a distributed force of minus 8.58. And this force is for the extra dead load in stage 8. The next stage is applying the temperature variation loads. So I select the temperature plus load case, and these loads will be applied to all of the structure. So I will select all of the beams here, properties, temperature, and these values, they are not they don't represent the absolute temperature, and they are only temperature variation. So I'm going to add 10 degrees here for the strong axis. Okay, and for the temperature minus, the members are already selected, so I'm going to add a temperature variation of -5 here. So I have applied all of the load cases here. In this stage, I'm going to check the member dead load and effective stages again. So as I already explained, for these members, the span ones, we will have the dead load from the stage 1, as you see that, and this one is the dead load, and the third one is the dead load is okay. And also we need to have them activated from stage 2. So if we check it from the spreadsheet here, advanced, as you see, they will be effective in stage 2. And also for the middle beams here, small ones, Control H. Firstly, we need to check their dead load, which is dead stage 5, and also they will be activated on stage 5. Yes, as you see here, they are effective at stage 5. So all of the definitions are okay. In the next stage, we will define our load combinations. So load cases, load combination generator. But before doing this, because this project is a staged construction, we firstly need to define our construction stages. So we have some load combinations which needs to be defined manually. So the first one will be stage 3. Stage 3, we will define it as a construction stage. We are going to define a stage 5. Construction stage. Stage 6. Stage 8. Construction stage. And stage 9. As construction stages. And in the next step, we need to define the stages here. So stage 3, stage 5, stage 6, stage 8, and stage 9. And after that, load factors. So for stage 3, we will have creep shrinkage, and the load factor is 0.8. We will have the dead load from the beams, and we will have the press dressing, that which is transferred. For stage 5, it will be again shrinkage 0.58. Dead stage 5 for the small beams. Pre-stressing. And finally additional dead for stage 5. So these are the load cases and factors for stage 5 combination. For stage 6, we only have the shrinkage with factor of 0.8 and the pre-stressing. For stage 8, we have the same shrinkage 0.8, pre-stressing 1, and dead load for stage 8. And stage 9 will be just creep shrinkage and pre-stressing. Okay, so as you see here, the staged construction load combinations were defined, and now we can use the load combination generator. We need to change the code to S6, so the load combinations according to S6 code will be generated. Other default values here are okay. Click next, and these are the list of load combinations that ADA is going to generate. In this project we don't have moving loads yet, so I'm going to deactivate this option. And as you see here, we need to put the check mark here because it is a pre-stressed concrete project, so we need to put the check mark here. Other options are okay. Click next. So these are the load combinations that ADA will generate, and if you want to remove any of them, just you can uncheck them here, remove the check mark, so ADA will not generate that load combination. And we click finish, and as you see here, ADA has generated the load combinations according to S6. We have a column here as required. As you see, all of these are already selected, all of the combinations to be analyzed. If you want to remove some of them and define them not to be analyzed, you can just remove the check mark. So in this case, these load combinations will not be analyzed. In this case, I'm going to analyze all of the load combinations here. So click OK. Next step is to define the concrete specification. So structure, specifications, and concrete. As you see here, I have some already defined. I'm going to delete them to show you how to define the new ones. So the first one will be a 6 design. And it's a design. To display other columns here, we need to select all of the entities here. And for the reinforcement bar, I'm going to change this to G3018. For the main reinforcement, we can use 20M and 25M. And I will define another one for verification, so it's 6. 606. It is verification. Okay. So here we defined our concrete specifications. Click OK. Okay. Yes, we have it here. And right now we need to assign these. Also in specifications concrete, we can define the other reinforcements here for the skin reinforcement or beam slab or other stuff. So we have this opportunity to use these options. For now it's fine. I'm going to use 10M, so okay. And after that, we need to, because it's a concrete project, we need to define the continuous systems. And ADA will use this continuous system to put the reinforcement and the cables inside the section. So as you see here, ADA automatically has built the continuous system. So if I go to continuous system activation, I activate it and click on the members. As you see, ADA sees that model as a one beam, and it will put the reinforcement and tendons continuously on this member. So to assign the design specification for our continuous system, we need to activate the continuous system, double click, and here we can assign a 6 design, and also we can assign the covers here that ADA will use to calculate the reinforcement. So the top cover I'm going to use 50 millimeters, and for the bottom cover 50, and for the left and right. So clicking OK. Now I've assigned my design specifications to my member. Next step is to add the cables, or if we want the reinforcing bars to the section. So to do that, we need to go to this rebar placement window. So as you see here, I'm going to activate this rebar placement and double click my member, save the project, and here is the member. We don't have anything right now on it, we don't have any strands, but we are going to add some strands to this member. First of all, we need to activate the view options, check the general to have all of the information. And also I'm going to generate some cross sections for this member. Generator, as you see here, is already defined, so it's okay. And these are the automatically created sections. We do not have any tendons and strands yet. You can always move these cross sections by using this tool here. So these are the cross sections. You can add or delete some of the cross sections from this spreadsheet here. These are the coordinates, so you can just delete them from here, or like this, just select them and press the delete button at the keyboard to delete the sections. Also, you can move the cross section or the detail if you want to have these a bit lower here on the screen. So just use this, click on it, select it, and bring it down here. So these options will help you to align the sections, or you can align them again from this spreadsheet. For example, I'm going to align them on -7,000. As you see, my sections are now a bit lower. Okay, now we are going to define the cable groups and the layouts. So we use the rebar placement menu, cable groups. I will use 6 layouts for this project. So each beam will have 2 strands, and totally we will have 6 strands for all of the continuous system here. So to add these layouts, we need to start to define them from here. So for example, the first one will be span 1, flat strand. Because it's not post tension, we will leave here blank. It will be only 1, and its coordinates inside the member, and it will be the local coordinates of the member. It's -20 to 20 millimeters, so it's almost in the center of the section. I will have only one. I will have only one here, one group of cable, which has 26 strands, and the strand type is J 270 half-inch. It is internal without groove, the layout, and it is initial pretensioning. The jacking force is 75%. We don't have any cones. And this is the definition of our first cable. The second one will be again span 1. This one will be up. Same. In this case, the number of strands in this tendon or cable will be 14. Same material. %75 of jacking. Okay. Now I'm going to define the span 2. Flat. This one will be -30 because we have much more strands here, so 30. And for span 2 flat, we have 42 strands. $75. Okay, so I'm going to copy this to span 2 up. minus 30 to 30. This one 22. Span 3 flat. Minus 20 to 20. And span 3 up, $20, 14 strands. Okay, so I have defined all 6 cables. In the next stage, I will add the layouts. So the first one will be straight mobile ends. The Z1 will be 60 millimeters, which is start point of the tendon, minus 1917. These values are the local coordinates of the member. Z2 and Y2, they will be 0. And for this one, it will be 27, 260. Same number, minus 1917. So as you see, the Z's here are the coordinates along the member longitudinally, and the Y's here is the elevation of the tendon in the section, and it's measured from the top fiber of the section. So here, as you see, we have defined the first span 1 flat layout here. For the second one, which is an upper one, it's not an straight tendon, so I'm going to use the generator from ADA to define this tendon. The first one, the first layout is okay, and we can always insert the values here. 60 millimeters, 328.7 for Y1, minus 1917 Y2, minus 3287, 10-240, 6720 for D2, and D3 is 10-240. So as you see here, you have the D's here and Y's here. The Z is the starting point of the tendon. So clicking OK. As you see here, ADA automatically has calculated the strands and their coordinates for span 1 up. And to save the time here in this project, I have defined the other 4 cables in this project, as you see. So these are the values here. You can input it in your project. For span 2 flat, span 2 up, this is the values for the tendon. Span 3 flat, again, it's only one row. And as you see, the Z values are changing because we are moving along the continuous system. And finally, span 3 up will be these coordinates to our strands. So using this dialog box, we defined all of the tendons here, and if I hit OK, as you see, ADA has placed the tendons or cables in the sections as we have defined before. Also, we can check out the dimensions here, so I'm going to use the view options and dimensions, put the check mark here. Okay, so here, as you see, ADA demonstrates the dimensions and the properties of the tendons. As you see here, span 1 up, the name of the tendon has 14 strands. Here, span 1 flat, 26 strands of G27 ½ inch. These are the dimensions. And if I look at the sections, you see here, now my tendons are all defined, and I can move the section. As you see here, the tendon is following the defined coordinates. For this section, we don't have any tendons yet. And here also you see that 60 millimeters that we already defined for starting point of our tendons. Okay, right now we have placed the tendons. Now we can close this window, save it, and now we can design the continuous system or concrete beam here. So I'm going to click this icon here, analysis and design. ADA started the analysis, close. And as you see, these two icons are already as default, they're selected. So just double click on the continuous system, and as you see, ADA has placed the extra main reinforcement and the stirrups. And if you check out the sections, as you see here, these are the reinforcements that ADA has placed for this section. As you see here, we have so many rebars, so maybe we have a problem here. This first support, I'm going to check that and solve that problem. So close this. If we check our moment diagram, let's say in ULS2, view options, MX. As you see here, I have a huge moment here. So from the beginning, we should have released this support. So I'm going to do it right now. Go to structural mode, select the support, and we need to release, X fixed and Z here. Okay, so run the project, design, close. So right now, if you check the moment diagram again, you see here we have corrected the problem. And if we check out the steel design, as you see here, everything is okay right now. These are the stirrups and tendons. To see the capacity of beam and comparing it with the limits, you can go to view options and beam diagrams. So you can have different kind of curves here. I'm going to remove some of them. So as you see here, these are the limits or strengths, limits of the section, and this is the moment. And as you see, our section or our design is more than enough for these loads, and that's because we have not applied the moving loads yet. For the shear also, you see it's okay, everything is fine. And ADA has placed the stirrups. Also here, ADA shows that number of main reinforcement here. It's 210 Ms. Section. And if I apply or we apply the moving loads in next sessions, we will have much more different results. We will have more heavier main reinforcement. But for purpose of this session, it was enough to know that how we put the strands, cables, define press-dressing tendons here, and construction stages for a press-dress concrete beam. We can also check the stress results for our concrete beam. So to bring up those results, we click this icon here, graphic results, and as you see here, these are the stresses in concrete. And other stages, and we have the ratio of cables here, stress of cables, deflection under different load stages, bending moments, shear forces, and also here you can select which part of the section you want to see the stresses. So as you see here, so the top of the section, the stresses coming from the slab and the beam itself. Here is the bottom of the section. The green lines are for slab maximum limit, and the yellows are the stress top of a slab. And if you just want to check the slab, as you see here, the stresses in the slab are in the limits of the green lines, and the stresses from the section are in the limits of a red line. So and the stresses are in acceptable range. And this is for stage 9. Okay, and also we can bring up the numerical results. For example, if you want to check for loss of press-dressing cables, you can go to results and loss of press-dressing cables. As you see here, we have the numerical results here. We have all of the results here, stresses due to creep, shrinkage, elastic shortening, and all of the numerical results are here. And this is the sum of the losses in the press-dressed tendons or press-dressed cables. We can also have the intermediate results here. And this spreadsheet includes the shrinkage and creep effect properties according to days, cumulative. So as you see here, we have the days, and these are the results for creep and shrinkage. And the other kind of results that we can check here is the stresses in different stages. These are numerical results. So if you want to check the stage 9 stresses here, you have all of the stresses here as numerical values, and you can always copy and paste these values to the Excel or other softwares. This is for different members, M1, M4, M2, M5, and M3. And you have the stresses at top and bottom of slab and section here. Also, you have the deflections for stage 9, and the position of the deflections, as you see here, is placed in this column. We can also check the general results here to have the information regarding the design, concrete design. So you have all the information here on all of the members. And as you see, for my small beams between the spans, I have problem with not bending. Bendings is okay, but because ADAR is showing them as yellow, so there's a problem in the design. I'm going to check the negative bending moment. As you see, it's okay. For shear force, as you see, we have a problem with shear force in those small beams. And the reason is, if I click OK, as you see, we have no shear reinforcements in this area. So to correct this, we can always add some stirrups in these parts, or we can move these stirrups in a way that we can have some shear reinforcements, extra shear reinforcement here. So what I'm going to do is select these stirrups, double click, and I'm going to move that forward. Let's say 27,000. And also for this one, I'm going to move it to left. Let's say 28,100 millimeter. Okay, 600 will be nice. Okay, this is just for an example to show you how we can change the placement of stirrups. You can also add their numbers or spacing. For this example, I'm just changing their placement. And for this support also, I'm going to add this. Let's say 60,100, a bit more. Okay, and this one, As you see, the syrups, they moved here. And if I check for design again, results, general results, as you see here, we have no yellow rows here again. So everything is fine. The design is okay for all of the members, for negative bending and shear axial force. And here you have the cable positions for the members. These members that you see here, I don't have any cables because these are these middle small beams. And this is the rebar placement for the last span beam. Okay. So we have seen a simple example on how to model and design a simple 3-span pre-stressed concrete beam. In the next session, we will talk about post-tensioning. So if you have any questions on this session, just let us know with this email or send us your email. Thank you very much.